So here are a couple of questions that we'll end with for this segment, because these are things that use the function notation but sort of carry us on to the next topic. We're going to draw a function, we're going to plot some points, and we're going to look at the issue of slope. That's really where calculus starts, is taking these curved objects and thinking about what does the slope of a curved object really mean. So we'll start by drawing a picture. This is most easily done with a calculator. That's not good. Most easily done with a calculator, and we'll go over that too. But it's fairly easy to plot a couple of points. For example, f of 0 is 0. That's easy enough to see. And f of 3 is 0. How did I know that? Well, I'm kind of cheating here. I can see that this factors as x times x minus 3. And so I know for sure that x equals 0 and x equals 3 are the x-intercepts. So those are easy points to plot. This guy should be a parabola going up, so this is going to be hard to draw with this pad, but I'll do my best. So it'll look kind of like that. Again, some kind of machine. There's a link in the custom content section of the of MyMathLab. There's a link to a graphing applet that'll draw the picture much better for you. But it's fairly easy to draw it because we know the shape, we know it's a parabola, and we know a couple of points on it. So if we know the shape and we know a couple of points, then we can usually get a pretty good idea. So here's a better drawing. This comes from the applet that's linked in the custom contents folder, so that we can use this to get a better picture for the rest of the problem. We want the point 2f of 2. Now I could, over here, figure out what f of 2 is. Because remember, the definition of the function was x squared minus 3x. So f of 2 should be 4 minus 6, which is negative 2. So I could say here this is negative 2, and I could plot the point, 2, negative 2. But notice that it hits the curve, right? That's the whole point. The f of something tells you the y-coordinate on the curve when the x is 2. So the same thing here, 3f of 3. Well, f of 3 is the y-coordinate on this curve when the x-coordinate is 3. And so that's right here. If I have the graph, I don't have to go back and figure these things out from the formula. The graph is a whole bunch of points already plotted, and so it's already done the hard work for me. So this, the line between these things is going to look kind of like this. It's a little hard to draw with this pad, but I'll do my best. So that's the line between the 2 points. I've drawn the 2 points. The idea here is that the slope of a line is actually easy to figure out. That's just rise over run. Right? So the slope, and we use m for slope for some reason, this is the rise over the run, so that's the change in y over the change in x. I'm using the triangle here. That's the Greek letter delta that stands for change. It goes way back to the Greeks. So the change in y is my rise. That the point rises 2 units, and the run is 1 unit. So since I have the graph here, I can just count. If I didn't have the graph, I could just do it from the coordinates. It would be the difference in the y coordinates is 2, and the difference in the x coordinates is 1. So I get a slope of 2. Now this gives me a rough idea of how this curve is shaped. I know that over here the curve is going up, and it's going up at a pretty steep rate, 2 to 1. Every 1 unit over, I'm going up 2. So it gives me a sense for how steep the thing is. What I really want to know, though, from a calculus point of view, is how steep is the curve really going up at a particular point. So, for example, right here at 2, the curve is on its way up. And the question is, how steep is the curve? How fast is it going up? The way that we deal with that from a calculus perspective is we imagine, we look really close around this point, And if you only look in that circle, the curve, the blue curve, actually looks fairly straight. So what I do is I imagine straightening out the blue curve so that it looks like a line. And I'm only looking inside this circle. So inside this circle, the blue curve looks straight, and then I straighten out the line. This line that I'm using to extend the blue curve is called the tangent line. Call this tangent to the curve. So I can actually find the steepness of that tangent line by just doing a regular rise over run slope. And the steepness of that tangent line then corresponds to the steepness of the curve at that point. Now, because this thing is curved, at different points, it'll have different steepnesses. Up here at x equals 3, for example, the curve is steeper than it was down here. Over here, at x equals 0, the curve actually has a negative steepness, a negative slope. So the curviness of this thing is indicated by the fact that every place you look, you have a different steepness, a different slope. But calculating that slope is actually just a rise over run calculation. So here's how I would do it. I would just do rise over run between these 2 points. Why did I pick these 2 points? Well, those are 2 points that I believe are in this circle that I drew. Right? So inside this little circle, my blue curve looks straight. Inside that circle are these 2 points. So if I figure out the y coordinates for these, we already figured out at 2 we have y coordinates -2. At 2.1, you need to use a calculator, so I'll do 2.1 squared minus 3 times 2.1, and I get -1.89. So the slope between those 2 points is hard to count because their numbers are all decimally, but it's easy to just subtract the x coordinates and the y coordinates. So this is the y coordinate subtracted, so that's the y coordinate for the first point, y coordinate for this point being subtracted, and then the corresponding x components. So I'm just finding rise over run slope, and if I do that, up here I have 0.11, and down here I have 0.1, so that's 1.1. So this guy's slope is about, well, the slope of the line there is 1.1. So all I know, I mean, again, the blue curve really isn't exactly straight, so I know that the slope of the curve here is about 1.1. I don't know what it is exactly, but it's about 1.1 that I'm getting by just doing a regular old slope calculation on the tangent line. Okay, so we'll continue this idea into the next section where we actually can produce formulas for finding slopes.